There's a stretch of river in southwest China where the canyon walls rise almost straight up, and the water at the bottom looks angry, dark, fast, and loud. When I first saw aerial footage of it, my brain didn't register a place to build a dam. It registered a place you leave alone. This is the Jinsha River, upstream of the Yangtze, and wedged into one of its narrowest, most violent sections is the Baihetan Dam. It's 289 meters tall, almost the height of the Eiffel Tower, and inside it are machines that, for a long time, sounded like a typo. 16 hydropower turbines, each rated at 1,000 megawatts, 1 million kilowatts per unit. If that number feels absurd, good, it is. Here's what you need to know up front. 16 gigawatts total installed capacity, second only to Three Gorges. Around 62.4 billion kilowatt hours of electricity a year, depending on water conditions. A project costs often cited around $30 to $35 billion in total investment. But the story isn't China built a big dam. The story is, how do you build a dam in a canyon like this and then build the most powerful hydropower units ever put into service without shaking the whole system apart? To answer that, we need the why first. China's energy geography is awkward in a way most countries never deal with. A huge share of electricity demand sits in the east. Dense cities, heavy industry, massive manufacturing clusters, but some of the best hydro resources are far inland in steep western river systems. So China's long-term strategy has been generate huge amounts of power where nature makes it cheap, then move that power thousands of kilometers to where people actually use it. Hydropower also does something wind and solar struggle with at scale. It can provide stable output and fast ramping. Basically, it helps keep the grid steady. Baihetan is a piece of that puzzle, a very large piece. And just to be clear, I'm not saying big dams are purely good. They never are. We'll get to the trade-offs later, but engineering-wise, this one is hard not to stare at. Problem number one, the mountain isn't one solid block. At Baihetan, you're not building on a nice uniform slab of rock. You're dealing with complex geology. Faults, fractures, and zones where water pressure can exploit weaknesses over decades. So engineers did something that sounds simple, but at this scale becomes insane. They performed extensive foundation treatment, drilling deep and injecting cement-based grout under pressure to seal fractures and reinforce the rock mass. If you want a mental image, think of a cracked piece of stone where water will always find the crack. Then imagine you're trying to seal that crack system, not in a countertop, but inside a cliff face. This isn't a single trick, it's thousands and thousands of targeted interventions until the foundation behaves like one stable system. Because with a dam this tall, the margin for A, it's probably fine, is basically zero. Problem number two, the turbines. The part that actually shocked me. A 1,000 megawatt hydropower unit isn't just bigger. It's a different category of mechanical stress. Hydraulic forces, vibration control, material fatigue, long-term erosion, and precision manufacturing, all stacked on top of each other. And there's a specific enemy here, cavitation. Cavitation is when pressure drops, create tiny vapor bubbles in fast-moving water, and those bubbles collapse violently against the blade surface. Over time, it can pit and eat away metal like the world's most stubborn microscopic sandblaster. Now Baihetan's turbine runner, the rotating heart of the unit, is enormous, roughly 8.6 meters in diameter, around 350 tons. Each unit handles on the order of hundreds of cubic meters of water per second, often cited around the 500 plus cubic meters per second range depending on operating point. That's enough to fill an Olympic swimming pool in about 5 seconds. Per turbine. And you want that to run reliably for decades. So how did they do it? From what's publicly discussed, it comes down to a few things: materials and surface engineering to resist cavitation and fatigue, blade and runner design optimized to reduce vibration and pressure fluctuation, manufacturing precision at ridiculous scale, machining and balancing a component the size of a room to tight tolerances. The key point isn't someone said it's impossible. That's too easy and usually not provable. The more accurate point is, nobody had put 1,000 megawatt hydro units into commercial operation before. The risk and complexity are real. Baihetan did. And that's why engineers around the world pay attention. Problem number three, heat. Inside the concrete. People hear concrete dam and think it's just pouring and waiting. But in megadams, concrete curing generates heat. If the core gets too hot and then cools unevenly, you get thermal stress and cracks. Cracks are not cosmetic. Cracks are a path for water, and water is patient. So the solution is controlled temperature management, embedding cooling systems and controlling placement schedules so the dam cures more evenly. Think of cooking a thick piece of food. You don't want the outside done, and the inside still undercooked, because the unevenness is the problem. With a dam, unevenness becomes internal stress. The goal is a structure that stays stable not just for a ribbon-cutting ceremony, but for generations. Once the dam produces power, the next challenge is moving it. China has built ultra-high voltage transmission corridors to send electricity long distances. Depending on the line and loading, losses are typically in the single-digit % range, often cited around 6 to 7% for very long-distance UHVDC links. So power generated deep in a canyon can end up stabilizing grids and feeding factories far away. That's the system part of this story. Not just building a dam, but plugging it into a national-scale energy machine. Now, trade-offs. Baihetan involved large-scale resettlement, often cited around 100,000 people. That means real families leaving real places, and that never lands cleanly, no matter how compensation is handled. Environmentally, any dam changes a river, sediment movement, fish migration patterns, downstream ecology. There are mitigation measures, fish protection strategies, sediment management approaches, but zero impact doesn't exist at this scale. So if anyone tries to sell you a megadam story as purely heroic or purely evil, they're simplifying it for a narrative. The reality is heavier than that. Here's where I land on it. Baihetan isn't just impressive because it's big. It's impressive because it's a clean energy project that required solving problems in geology, materials, manufacturing, and grid integration at a scale where small mistakes don't stay small. And honestly, the 1,000 megawatt turbine units are the detail I think people will remember, not because they're a symbol, but because they're proof that the engineering supply chain, design, metallurgy, machining, quality control can now hit targets that used to be theoretical. If you want, in the next video I can break down one of China's other so-called impossible builds, like the sea-crossing bridge tunnels or the ultra-high voltage lines that make projects like Baihetan usable. Now I'm curious, if your country had one site where you could build a single massive clean energy project, hydro, nuclear, solar, wind, what would you choose and why? Tell me in the comments. And if you want more deep dives like this, subscribe.